This question states if an element has sigma x equals 50 megapascals, sigma y equals minus 10 megapascals, and tau xy equals 10 megapascals, what are in-plane principal stresses and what is the associated angle of rotation theta p? So for this problem, what we're going to do is use Colab, use Python to plot all the angles of rotation, at least within a specified limit, and be able to figure out where we have the maximum normal stresses. That's what we're looking for when we say principal stresses. At the state of principal stress, or the state of principal stress is however you want to write it or say it, we can say that the shear stress is also equal to zero. So let's go ahead and take a look at the Colab that we can use for this problem. We'll go ahead and go to the website where we have session 18 and then a little bit of scrolling to find the session 18 Colab IPython. And for this example, you might want to copy it into your own Google Drive. Here, I'm not going to save the work, so I'm just going to run it right in the Colab that came up with the click. So first things first, we're going to run this cell. We're going to say run anyway, and that's just getting the NumPy library and matplotlib library in. We can go down, and 18.1 is actually very similar, and it has the question, what are in-plane principal stresses, and what is the associated angle of rotation to get to this state of in-plane principal stresses. What we need to do is plug in the appropriate sigma x, sigma y, and tau xy. In this case, we have sigma y equal to 50 megapascals, sigma x equal to 50 megapascals, sigma y equal to minus 10 megapascals, and tau xy equal to 10 megapascals. So we'll go ahead and we'll plug in 50, stays the same. This is sigma y is going to be minus 10, and tau xy will be 10. Okay, so we're set there. And what we see here is it's going to go through angles 0 to 180 with quite a few points selected, 10,000, and then it will plot the arrays of results where we have the tau x, y, x prime, y prime, for example, versus angle. We have the sigma x prime versus the angles, and we have sigma y prime versus the angles. Okay, so let's go ahead, and we're using the generalized transformation equations that we've described previously. So we can click on the arrow or hit Control Enter, and we get some results. What do we see here? Well, we can, let's see, yep, okay, so here is the sigma x prime, and we see that I'm having, let me see if I can move this down a little bit so that we can move this. Yep, good. So we have our starting sigma x at 0 degrees of 50 megapascals. So that's, good simple check to make that when you have 0 rotation, you get what you put in. So at 0 rotation, we got 50 megapascals. We got the tau x prime y prime of yes, that's right, of 10 megapascals. Good. And for the sigma y prime, we got the starting at minus 10. I was getting confused between 10 and minus 10. I was like, what happened? And so I had a moment of pause. Okay, so these look reasonable. And if we look at values, we can see that maybe we get, a little bit above 50 megapascals for a maximum. Okay, and at a minimum, it gets maybe a little bit below negative 10. megapascals. And if we kind of look here, maybe this is around 10-ish degrees. Okay, and maybe this is around 100, maybe a little bit to the left of 100 degrees. And we see that at these corresponding angles around 10 degrees that the tau x prime y prime is in fact 0. And we see that at about 100 degrees, the tau x prime y prime is in fact 0. So that's a good sign that we're looking for our in-plane principal stresses. And sigma y prime is out of phase with sigma x prime. It goes a little bit below -10 at megapascals at 10 degrees, and it comes up a little bit above 50 megapascals at about 100 degrees. Okay? Now, we can use this code further down this other cell to actually tell us the maximums for sigma x and minimum for sigma x and maximum for sigma y prime and minimum for sigma y prime. So max sigma x prime, min sigma x prime. And it's essentially just going through the array to find of the calculated values to find the maximum, and then it spits out what the angle is there too. So make sure you hit the play button here or control enter, because it was previously putting out results for a different problem. And so we see that max sigma x prime is 52 megapascals with a rotation of 9.2 degrees, so we were saying around 10. We were saying a little bit above 50, and the minimum x prime, sigma x prime, is going to be at minus 11.6 megapascals, so a little bit below 10, minus 10, and that happens at 99.2 degrees. And then sigma y prime is going to be, the max sigma y prime is at 52 megapascals, and that's at a different angle of rotation than what we had for sigma x prime, as was the minimum sigma x prime. And we see the minimum sigma y prime is at minus 11.6 megapascals, and that's at a rotation angle of 9.2 degrees. So let's come back to the slides and jot down a few things. It's often helpful to plot these graphs, which we've done, and to take a look and make sure that things are making sense. Like we said, we started at 50 megapascals for sigma x. We did. There, we started at minus 10 megapascals for sigma y. Boom, we did. And we can paste in from the Colab the reported values. And we see that we have a max sigma x, again, we have a min sigma x, we have max sigma y, min sigma y, and the appropriate rotation angles. What does this look like on an element? Well, let's draw another element, and this one is maybe rotated a little bit closer to 10 degrees than this one was. And so we'll say that's theta P1, 9.2 degrees. And this was the x direction originally. Now this is the x prime direction coming out of this face, and sigma x prime will be coming out of this face, right? So you can see sigma x was aligned with the horizontal previously, and now sigma x prime is up at an angle. And this was determined numerically, essentially through trial and error type method, and then we looked at finding the maximum of the outputs. The sigma x prime value is given here as 51.6 megapascals, and so we could write that there if we like, or you could even write it right there, but you get the idea. Y prime is 90 degrees from sigma x, or from x prime, and we have this compressive stress that we've written out for the minimum sigma y, right, corresponding to the 9.2 degrees, which is what we have here. So sigma y prime is minus 11.6 megapascals, so this would be 11.6 megapascals with the arrow drawn the direction shown. Now, what happens if we look at this 99.2 degree rotation? Well, that's 90 degrees out of phase, or 90 degrees off from the sigma p1. So sigma p2 comes out over here. And what does that mean for the coordinate system? Well, um, it means that we have now this x2 prime essentially coming out of the y prime, and sigma x uh, 2 prime is the minus 11.6. Look, and that lines up quite nicely, right? We already saw this was compressive in that direction. And y prime 2 is 90 degrees off from x prime 2, or x2 prime, however you want to say it. And we see that there is a given value for the maxima y that is at 99.2 degrees. So again, that's going to be 51.6 megapascals, what you see there. So using this trial and error approach is helpful to be able to figure out what is happening with the in-plane principal stresses and finding the angles associated with their rotation. I hope you find this example helpful. Thank you.